Unit 1 Some basic concepts of chemistry. After studying this unit, you will be able to appreciate the contribution of India in the development of chemistry, understand the role of chemistry in different spheres of life, explain the characteristics of three states of matter, classify different substances into elements, compounds, and mixtures, use scientific notations and determine significant figures, differentiate between precision and accuracy, define SI base units and convert physical quantities from one system of units to another, explain various laws of chemical combination, appreciate significance of atomic mass, average atomic mass, molecular mass, and formula mass, describe the terms mole and molar mass, calculate the mass percent of component elements constituting a compound, determine empirical formula and molecular formula for a compound from the given experimental data, and perform the stoichiometric calculations. Chemistry is the science of molecules and their transformations. It is the science not so much of the 100 elements but of the infinite variety of molecules that may be built from them. Roald Hoffmann science can be viewed as a continuing human effort to systematize knowledge for describing and understanding nature. You have learned in your previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, formation of vinegar from sugarcane juice on keeping for prolonged time, and rusting of iron are some of the examples of changes which we come across many times. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies the preparation, properties, structure, and reactions of material substances is called chemistry. Development of chemistry. Chemistry, as we understand it today, is not a very old discipline. Chemistry was not studied for its own sake, rather it came up as a result of search for two interesting things: a philosopher's stone, paras, which would convert all baser metals, e.g., iron and copper, into gold; two, elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of life. Chemistry developed mainly in the form of alchemy and iatrochemistry during 1300 to 1600 CE. Modern chemistry took shape in the 18th century Europe, after a few centuries of alchemical traditions which were introduced in Europe by the Arabs. 2020 to 21 Chemistry. Other cultures, especially the Chinese and the Indian, had their own alchemical traditions. These included much knowledge of chemical processes and techniques. In ancient India, chemistry was called Rasayan Shastra, Rastantra, Ras Kriya, or Rasvidya. It included metallurgy, medicine, manufacture of cosmetics, glass, dyes, etc. Systematic excavations at Mohenjo-daro in Sindh and Harappa in Punjab prove that the story of development of chemistry in India is very old. Archaeological findings show that baked bricks were used in construction work. It shows the mass production of pottery, which can be regarded as the earliest chemical process, in which materials were mixed, molded and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been used in the construction work. It contains lime, sand, and traces of CaCO3. Harappans made faience, a sort of glass which was used in ornaments. They melted and forged a variety of objects from metals, such as lead, silver, gold, and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glass objects were found in Maski in South India, 1000-900 BCE, and Hastinapur and Taxila in North India, 1000-200 BCE. Glass and glazes were colored by addition of coloring agents like metal oxides. Copper metallurgy in India dates back to the beginning of Chalcolithic cultures in the subcontinent. There are much archaeological evidences to support the view that technologies for extraction of copper and iron were developed indigenously. According to Rigveda, tanning of leather and dyeing of cotton were practiced during 1000-4000 BCE. The golden gloss of the black polished ware of northern India could not be replicated and is still a chemical mystery. These wares indicate the mastery with which kiln temperatures could be controlled. Kautilya's Arthashastra describes the production of salt from sea. A vast number of statements and material described in the ancient Vedic literature can be shown to agree with modern scientific findings. Copper utensils, iron, gold, silver ornaments, and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Sushruta Samhita explains the importance of alkalis. The Charaka Samhita mentions ancient Indians who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin and zinc, the sulfates of copper, zinc, and iron and the carbonates of lead and iron. Rasopanishada describes the preparation of gunpowder mixture. Tamil texts also describe the preparation of fireworks using sulfur, charcoal, saltpetre, i.e., potassium nitrate, mercury, camphor, etc. Nagarjuna was a great Indian scientist. He was a reputed chemist, an alchemist, and a metallurgist. His work Rasratnakar deals with the formulation of mercury compounds. He has also discussed methods for the extraction of metals, like gold, silver, tin, and copper. A book, Arsarnavam, appeared around 800 CE. It discusses the uses of various furnaces, ovens, and crucibles for different purposes. It describes methods by which metals could be identified by flame color. Chakrapani discovered mercury sulfate. The credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredients for making soap. Indians began making soaps in the 18th century CE. Oil of Eranda and seeds of mahua plant and calcium carbonate were used for making soap. The paintings found on the walls of Ajanta and Ellora, which look fresh even after ages, testify to a high level of science achieved in ancient India. Varamir's Brihat Samhita is a sort of encyclopedia, which was composed in the 6th century CE. It informs about the preparation of glutinous material to be applied on walls and roofs of houses and temples. It was prepared entirely from extracts of various plants, fruits, seeds, and barks, which were concentrated by boiling, and then treated with various resins. It will be interesting to test such materials scientifically and assess them for use. 2020-21 Some basic concepts of chemistry. 3. A number of classical texts, like Atharvaveda, 1000 BCE, mention some dye stuff. The material used were turmeric, madder, sunflower, orpiment, cochineal, and lac. Some other substances having tinting property were kampalsika, padanga and jatuka. Varamir's Brihat Samhita gives references to perfumes and cosmetics. Recipes for hair dyeing were made from plants, like indigo, and minerals like iron power, black iron or steel, and acidic extracts of sour rice gruel. Gandayokli describes recipes for making scents, mouth perfumes, bath powders, incense and talcum powder. Paper was known to India in the 17th century, as account of Chinese traveler Yixing describes. Excavations at Taxila indicate that ink was used in India from the 4th century. Colors of ink were made from chalk, red lead, and minimum. It seems that the process of fermentation was well known to Indians. Vedas and Kautilya's Arthashastra mention about many types of liquors. Charaka Samhita also mentions ingredients, such as barks of plants, stem, flowers, leaves, woods, cereals, fruits and sugar cane for making asavas. The concept that matter is ultimately made of indivisible building blocks, appeared in India a few centuries BCE as a part of philosophical speculations. Acharyakanda, born in 600 BCE, originally known by the name Kashyap, was the first proponent of the atomic theory. He formulated the theory of very small indivisible particles, which he named Paramanu, comparable to atoms. He authored the text Vaishika Sutras. According to him, all substances are aggregated form of smaller units called atoms, Paramanu, which are eternal, indestructible, spherical, supersensible, and in motion in the original state. He explained that this individual entity cannot be sensed through any human organ. Kanda added that there are varieties of atoms that are as different as the different classes of substances. He said these, paramino, could form pairs or triplets, among other combinations, and unseen forces cause interaction between them. He conceptualized this theory around 2,500 years before John Dalton, 1766 to 1844. Charaka Samhita is the oldest Ayurvedic epic of India. It describes the treatment of diseases. The concept of reduction of particle size of metals is clearly discussed in Charaka Samhita. Extreme reduction of particle size is termed as nanotechnology. Charaka Samhita describes the use of plasma of metals in the treatment of ailments. Nowadays, it has been proved that plasmas have nanoparticles of metals. After the decline of alchemy, iatrochemistry reached a steady state, but it too declined due to the introduction and practice of Western medicinal system in the 20th century. During this period of stagnation, pharmaceutical industry based on Ayurveda continued to exist, but it too declined gradually. It took about 100 to 150 years for Indians to learn and adopt new techniques. During this time, foreign products poured in. As a result, indigenous traditional techniques gradually declined. Modern science appeared in Indian scene in the later part of the 19th century. By the mid-19th century, European scientists started coming to India and modern chemistry started growing. From the above discussion, you have learned that chemistry deals with the composition, structure, properties, and interaction of matter and is of much use to human beings in daily life. These aspects can be best described and understood in terms of basic constituents of matter that are atoms and molecules. That is why, chemistry is also called the science of atoms and molecules. Can we see, weigh, and perceive these entities, atoms and molecules? Is it possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and the number of these particles? We will get the answer of some of these questions in this unit. We will further describe how physical properties of matter can be quantitatively described using numerical values with suitable units. 2020 to 21 for Chemistry 1.1 Importance of chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas, such as weather patterns, functioning of brain and operation of a computer, production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including new material. Chemistry contributes in a big way to the national economy. It also plays an important role in meeting human needs for food, healthcare products, and other material aimed at improving the quality of life. This is exemplified by the large-scale production of a variety of fertilizers, improved variety of pesticides and insecticides. Chemistry provides methods for the isolation of life-saving drugs from natural sources and makes possible synthesis of such drugs. Some of these drugs are cisplatin and Taxol, which are effective in cancer therapy. The drug AZT, azithromycin, is used for helping AIDS patients. Chemistry contributes to a large extent in the development and growth of a nation. With a better understanding of chemical principles, it has now become possible to design and synthesize new material having specific magnetic, electric, and optical properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods, like acids, alkalis, dyes, polymer metals, etc. These industries contribute in a big way to the economy of a nation and generate employment. In recent years, chemistry has helped in dealing with some of the pressing aspects of environmental degradation with a fair degree of success. Safer alternatives to environmentally hazardous refrigerants, like CFCs, chlorofluorocarbons, responsible for ozone depletion in the stratosphere, have been successfully synthesized. However, many big environmental problems continue to be matters of grave concern to the chemists. One such problem is the management of the greenhouse gases, like methane, carbon dioxide, etc. Understanding of biochemical processes, use of enzymes for large-scale production of chemicals and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country, like India, needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. 1.2 Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristics of the states of matter, which you learned in your previous classes. 1.2.1 States of matter. You are aware that matter can exist in three physical states, viz. solid, liquid and gas. The constituent particles of matter in these three states can be represented as shown in Fig. 1.1. Particles are held very close to each other in solids in an orderly fashion and there is not much freedom of movement. In liquids, the particles are close to each other but they can move around. However, in gases, the particles are far apart as compared to those present in solid or liquid states and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibit the following characteristics. I. Solids have definite volume and definite shape. 2. Liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. 2020-21 Some basic concepts of chemistry. 5 Fig. 1.1 Arrangement of particles in solid, liquid, and gaseous state. 3. Gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure. Solid, liquid, gas. On heating, a solid usually changes to a liquid, and the liquid on further heating changes to gas, or vapor. In the reverse process, a gas on cooling liquefies to the liquid and the liquid on further cooling freezes to the solid. 1.2.2 Classification of matter. In Class 9, Chapter 2, you have learned that at the macroscopic or bulk level, matter can be classified as mixture or pure substance. These can be further subdivided as shown in Fig. 1.2. When all constituent particles of a substance are same in chemical nature, it is said to be a pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substances which may be present in it in any ratio. Hence, their composition is variable. Pure substances forming mixture are called its components. Many of the substances present around you are mixtures. For example, sugar solution in water, air, tea, etc., are all mixtures. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of components of the mixture are uniformly distributed throughout. Fig. 1.2 Classification of matter. The bulk of the mixture and its composition is uniform throughout. Sugar solution and air are the examples of homogeneous mixtures. In contrast to this, in a heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixtures of salt and sugar, grains and pulses along with some dirt, often stone pieces, are heterogeneous mixtures. You can think of many more examples of mixtures which you come across in the daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods, such as simple handpicking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixtures. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water, and glucose are some examples of pure substances. Glucose contains carbon, hydrogen, and oxygen in a fixed ratio, and its particles are of same composition. Hence, like all other pure substances, glucose has a fixed composition. Also, its constituents carbon, hydrogen and oxygen cannot be separated by simple physical methods. Pure substances can further be classified into elements and compounds. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atoms and molecules from the 2020 to 21-6 chemistry previous classes, however, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc., are some examples of elements. All atoms are of one type. However, the atoms of different elements are different in nature. Some elements, such as sodium or copper, contain atoms as their constituent particles, whereas, in some others, the constituent particles are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen, and oxygen gases consist of molecules, in which two atoms combine to give their respective molecules. This is illustrated in Fig. 1.3. Fig. 1.3, a representation of atoms and molecules. When two or more atoms of different elements combine together in a definite ratio, the molecule of a compound is obtained. Moreover, the constituents of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Examples of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in Fig. 1.4. Note that a water molecule comprises two hydrogen atoms and one oxygen atom. Similarly, a molecule of carbon dioxide contains two oxygen atoms combined with one water molecule, H2O, carbon dioxide molecule, CO2. Fig. 1.4, a depiction of molecules of water and carbon dioxide carbon atom. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen are gases, whereas the compound formed by their combination, i.e., water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a supporter of combustion, but water is used as a fire extinguisher. 1.3 Properties of matter and their measurement. 1.3.1 Physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into two categories: physical properties, such as color, odor, melting point, boiling point, density, etc., and chemical properties, like composition, combustibility, reactivity with acids and bases, etc. Physical properties can be measured or observed without changing the identity or the composition of the substance. The measurement or observation of chemical properties requires a chemical change to occur. Measurement of physical properties does not require occurrence of a chemical change. The examples of chemical properties are characteristic reactions of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. In the 2020-21 Some Basic Concepts of Chemistry 7 following section, we will learn about the measurement of physical properties. 1.3.2 Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter, such as length, area, volume, etc., are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 m. Here, 6 is the number and m denotes meter, the unit in which the length is measured. Earlier, two different systems of measurement, i.e., the English system and the metric system, were being used in different parts of the world. The metric system, which originated in France in late 18th century, was more convenient as it was based on the decimal system. Late, need of a common standard system was felt by the scientific community. Such a system was established in 1960 and is discussed in detail below. 1.3.3 The International System of Units, SI. The International System of Units, in French Le Système International des Unités abbreviated as SI, was established by the 11th General Conference on Weights and Measures, CGPM from Conference Générale des Poids et Mesures. The CGPM is an intergovernmental treaty organization created by a diplomatic treaty known as maintaining the national standards of measurement. The system of units, including unit definitions, keeps on changing with time. Whenever the accuracy of measurement of a particular unit was enhanced substantially by adopting new principles, member nations of Meter Treaty, signed in 1875, agreed to change the formal definition of that unit. Each modern industrialist country, including India, has a National Metrology Institute, NMI, which maintains standards of measurements. This responsibility has been given to the National Physical Laboratory, NPL, New Delhi. This laboratory establishes experiments to realize the base units and derived units of measurement and maintains national standards of measurement. These standards are periodically intercompared with standards maintained at other national metrology institutes in the world, as well as those established at the International Bureau of Standards in Paris. Meter Convention, which was signed in Paris in 1875. The SI system has 7 base units and they are listed in Table 1.1. These units pertain to the 7 fundamental scientific quantities. The other physical quantities, such as speed, volume, density, etc., can be derived from these quantities. Table 1.1 Base physical quantities and their units. Base physical quantity: length, mass, time, electric current, thermodynamic temperature, amount of substance, luminous intensity. Symbol for quantity LMTIT and for name of SI unit: meter, kilogram, second, ampere, Kelvin, mole, candela. Symbol for SI unit: mkg, SAK, mole. CD 2020-21-8 Chemistry. The definitions of the SI base units are given in Table 1.2. The SI system allows the use of prefixes to indicate the multiples or submultiples of a unit. These prefixes are listed in Table 1.3. Let us now quickly go through some of the quantities which you will be often using in this book. Unit of length, unit of mass, unit of time, unit of electric current, unit of thermodynamic temperature, unit of amount of substance, unit of luminous intensity. Table 1.2 Definitions of SI base units: meter, kilogram, second, ampere, Kelvin, mole, candela. The meter, symbol M, is the SI unit of length. It is defined by taking the fixed numerical value of the speed of light in vacuum c to be 299792458 when expressed in the unit ms1, where the second is defined in terms of the cesium frequency VCS. The kilogram, symbol kg, is the SI unit of mass. It is defined by taking the fixed numerical value of the Planck constant h to be 6.62607015 times 1034 when expressed in the unit JS, which is equal to kgm2s1, where the meter and the second are defined in terms of C and VCS. The second, symbol S, is the SI unit of time. It is defined by taking the fixed numerical value of the cesium frequency VCS, the unperturbed ground state hyperfine transition frequency of the cesium-133 atom, to be 919.263.1770 when expressed in the unit Hertz, which is equal to S1. The ampere, symbol A, is the SI unit of electric current. It is defined by taking the fixed numerical value of the elementary charge E to be 1.60217663 times 1019 when expressed in the unit C, which is equal to as, where the second is defined in terms of VCS. The Kelvin, symbol K, is the SI unit of thermodynamic temperature. It is defined by taking the fixed numerical value of the Boltzmann constant K to be 1.380649 times 1023 when expressed in the unit JK1, which is equal to kgm2s2k1 where the kilogram, meter, and second are defined in terms of H, C and VCS. The mole, Symbol mole is the SI unit of amount of substance. 1 mole contains exactly 6.022140076 times 1023 elementary entities. This number is the fixed numerical value of the Avogadro constant, Na, when expressed in the unit mole1 and is called the Avogadro number. The amount of substance, symbol N, of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, any other particle or specified group of particles. The candela, symbol CD, is the SI unit of luminous intensity in a given direction. It is defined by taking the fixed numerical value of the luminous efficacy of monochromatic radiation of frequency 540 times 1012 Hz, kCD, to be 683 when expressed in the unit LMW1, which is equal to CDSRW1, or CDSRKG1M2S3, where the kilogram, meter, and second are defined in terms of H, C and V. CS 2020-21 Some Basic Concepts of Chemistry 9 Table 1.3 Prefixes used in the SI system. Multiple prefix symbol 1024 1021 1018 1015 1012 1009 106 103 102 10110 102 103 106 109 1012 1015 1018 1021 1024 Yocto Y Zepto Z Atto Femto F Pico P Nano N Micro Milli M Centi C Deci D Decada Hecto H Kilo K Mega M Giga G Terra T Peta P Exa E Zeta Z Yada Y 1.3.4 Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas, its weight may vary from one place to another due to change in gravity. You should be careful in using these terms. The mass of a substance can be determined accurately in the laboratory by using an analytical balance, Fig 1.5. The SI unit of mass as given in Table 1.1 is kilogram. However, its fraction named as gram, 1 kilogram equals 1000 grams, is used in laboratories due to the smaller amounts of chemicals used in chemical reactions. 1.3.5 Volume is the amount of space occupied by a substance. It has the units of length, 3. So in Fig 1.5 analytical balance SI system, volume has units of m3. But again, in chemistry laboratories, smaller volumes are used. Hence, volume is often denoted in cm3 or dm3 units. A common unit, liter, L, which is not an SI unit, is used for measurement of volume of liquids. 1 L equals 1000 ml, 1000 cubic centimeters equals 1 dm3. Fig 1.6 helps to visualize these relations. Fig 1.6 Different units used to express volume 2020-2110 Chemistry in the laboratory. The volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of a solution. These measuring devices are shown in Fig 1.7. Fig 1.7 Some volume measuring devices 1.3.6 Density. The two properties mass and volume discussed above are related as follows. Density equals mass. Volume density of a substance is its amount of mass per unit volume. So, SI units of density can be obtained as follows. SI unit of density equals SI unit of mass. SI unit of volume kg equals m3 or kg m3. This unit is quite large and a chemist often expresses density in gcm3, where mass is expressed in gram and volume is expressed in cm3. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. 1.3.7 Temperature. There are three common scales to measure temperature: degree C, degree Celsius, degree F, degree Fahrenheit, and K, Kelvin. Here, K is the SI unit. The thermometers based on these scales are shown in Fig 1.8. Generally, the thermometer with Celsius scale are calibrated from 0 degrees to 100 degrees, where these two temperatures are the freezing point and the boiling point of water, respectively. The Fahrenheit scale is represented between 32 degrees to 212 degrees. The temperatures on two scales are related to each other by the following relationship: degree F equals 9, degree C, plus 32.5. The Kelvin scale is related to Celsius scale as follows: K equals degree C plus 273.15. It is interesting to note that temperature below 0 degrees Celsius, i.e., negative values, are possible in Celsius scale, but in Kelvin scale, negative temperature is not possible. Fig 1.8 Thermometers using different temperature scales. 1.4 Uncertainty in measurement. Many a time in the study of chemistry, one has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers conveniently, and 2020-21 Some basic concepts of chemistry. Reference standard. After defining a unit of measurement such as the kilogram or the meter, scientists agreed on reference standards that make it possible to calibrate all measuring devices. For getting reliable measurements, all devices such as meter sticks and analytical balances have been calibrated by their manufacturers to give correct readings. However, each of these devices is standardized or calibrated against some reference. The mass standard is the kilogram since 1889. It has been defined as the mass of platinum iridium, PTIR, cylinder that is stored in an airtight jar at International Bureau of Weights and Measures in Sèvres, France. PTIR was chosen for this standard because it is highly resistant to chemical attack and its mass will not change for an extremely long time. Scientists are in search of a new standard for mass. This is being attempted through accurate determination of Avogadro constant. Work on this new standard focuses on ways to measure accurately the number of atoms in a well-defined mass of sample. One such method, which uses X-rays to determine the atomic density of a crystal of ultra-pure silicon, has an accuracy of about 1 part in 106 but has not yet been adopted to serve as a standard. There are other methods, but none of them are presently adequate to replace the PTIR cylinder. No doubt, changes are expected within this decade. The meter was originally defined as the length between two marks on a PTIR bar kept at a temperature of 0 degrees Celsius, 273.15 K. In 1960 the length of the meter was defined as 1.6507637 times 106 times the wavelength of light emitted by a krypton laser. Although this was a cumbersome number, it preserved the length of the meter at its agreed value. The meter was redefined in 1983 by CGPM as the length of path traveled by light in vacuum during a time interval of 1/299,792,458 of a second. Similar to the length and the mass, there are reference standards for other physical quantities. 11. Present the data realistically with certainty to the extent possible. These ideas are discussed below in detail. 1.4.1 Scientific notation. As chemistry is the study of atoms and molecules, which have extremely low masses and are present in extremely large numbers, a chemist has to deal with numbers as large as 602, 200,000,000,000,000,000,000,000,000,000,000,000,000,000 for the molecules of 2 grams of hydrogen gas, or as small as 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 Planck's constant, speed of light, charges on particles, etc., involve numbers of the above magnitude. It may look funny for a moment to write or count numbers involving so many zeros, but it offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication, or division with such numbers. You can write any two numbers of the above type and try any one of the operations you like to accept as a challenge, and then, you will really appreciate the difficulty in handling such numbers. This problem is solved by using scientific notation for such numbers, i.e., exponential notation, in which any number can be represented in the form n times 10n, where n is an exponent having positive or negative values and n is a number, called digit term, which varies between 1.000 and 9.999. Thus, we can write 232.508 as 2.32508 times 102 in scientific notation. Note that while writing it, the decimal had to be moved to the left by 2 places, and same is the exponent, 2, of 10 in the scientific notation. Similarly, 0.00016 can be written as 1.6 times 104. Here, the decimal has to be moved 4 places to the right, and 4 is the exponent in the scientific notation. While performing mathematical operations on numbers expressed in scientific notations, the following points are to be kept in mind. 2020 to 2112, chemistry multiplication and division. These two operations follow the same rules which are there for exponential numbers, i.e., 5.6 times 105 times 6.9 times 108 equals 5.6 times 6.9, 105 plus 8 equals 5.6 times 6.9, times 1013 equals 38.64 times 1013 equals 3.864 times 1014, 9.8 times 10 to 2 times 2.5 times 10 to 6 equals 9.8 times 2.5, 10-2 plus, minus 6, equals 9.8 times 2.5, 10-2-6 equals 24.50 times 10 to 8 equals 2.450 times 10 to 7, 2.7 times 10-3 5.5 times 104 equals 2.7 divided by 5.5, 10 to 3, 4 equals 0.4909 times 10 to 7 equals 4.909 times 10 to 8. Addition and subtraction for these two operations. First, the numbers are written in such a way that they have the same exponent. After that, the coefficients, digit terms, are added or subtracted as the case may be. Thus, for adding 6.65 times 104 and 8.95 times 103, exponent is made same for both the numbers. Thus, we get 6.65 times 104, plus 0.895 times 104, then, these numbers can be added as follows: 6.65 plus 0.895, times 104 equals 7.545 times 104. Similarly, the subtraction of two numbers can be done as shown below: 2.5 times 102, 4.8 times 103, equals 2.5 times 102, 0.48 times 102, equals 2.50.48, times 102 equals 2.02 times 102. 1.4.2 Significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitation of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using a platform balance and it comes out to be 9.4 grams. On measuring the mass of this object on an analytical balance, the mass obtained is 9.4213 guaranis. The mass obtained by an analytical balance is slightly higher than the mass obtained by using a platform balance. Therefore, digit 4 placed after decimal in the measurement by platform balance is uncertain. The uncertainty in the experimental or the calculated values is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus 1 which is estimated or uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. Thus, if we write a result as 11.2 ml, we say the 11 is certain and 2 is uncertain, and the uncertainty would be plus 1 in the last digit. Unless otherwise stated, an uncertainty of plus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures. These are stated below. 1. All non-zero digits are significant. For example, in 285 centimeters, there are 3 significant figures, and in 0.25 ml, there are 2 significant figures. 2. Zeros preceding to first non-zero digit are not significant. Such zero indicates the position of decimal point. Thus, 0.03 has one significant figure and 0.0052 has two significant figures. 3. Zeros between two non-zero digits are significant. Thus, 2.005 has four significant figures. 4. Zeros at the end or right of a number are significant, provided they are on the right side of the decimal point. For example, 0.200 grams has three significant figures. But, if otherwise, the terminal zeros are not significant if there is no decimal point. For example, 100 has only one significant figure, but 100 has three significant figures and 100.0 has four significant figures. Such numbers are better represented in scientific notation. We can express the number 100 as 1 times 102 for one significant figure, 1.0 times 102 for two significant figures and 1.00 times 102 for three significant figures. 2020-21 Some Basic Concepts of Chemistry 13. 5. Counting the numbers of object. For example, 2 balls, or 20 eggs, have infinite significant figures as these are exact numbers and can be represented by writing infinite number of zeros after placing a decimal, i.e., 2 equals 2.0000000 or 20 equals 20.0000000. In numbers written in scientific notation, all digits are significant, e.g., 4.01 times 102 has three significant figures, and 8.256 times 103 has four significant figures. However, one would always like the results to be precise and accurate. Precision and accuracy are often referred to while we talk about the measurement. Precision refers to the closeness of various measurements for the same quantity. However, accuracy is the agreement of a particular value to the true value of the result. For example, if the true value for a result is 2.00 grams and student A takes two measurements and reports the results as 1.95 grams and 1.93 grams. These values are precise as they are close to each other but are not accurate. Another student B repeats the experiment and obtains 1.94 grams and 2.05 grams as the results for two measurements. These observations are neither precise nor accurate. When the third student C repeats these measurements and reports 2.01 grams and 1.99 grams as the result, these values are both precise and accurate. This can be more clearly understood from the data given in Table 1.4. Table 1.4 Data to illustrate precision and accuracy measurements /G Student A Student B Student C 1.95 1.94 2.012 1.93 2.05 1.99 Average G 1.940 1.995 2.000 Addition and subtraction of significant figures. The result cannot have more digits to the right of the decimal point than either of the original numbers. 12.11 18.0 1.012 31.122 Here, 18.0 has only one digit after the decimal point and the result should be reported only up to one digit after the decimal point, which is 31.1. Multiplication and division of significant figures. In these operations, the result must be reported with no more significant figures as in the measurement with a few significant figures. 2.5 times 1.25 equals 3.125. Since 2.5 has two significant figures, the result should not have more than two significant figures, thus, it is 3.1. While limiting the result to the required number of significant figures as done in the above mathematical operation, one has to keep in mind the following points for rounding off the numbers 1. If the rightmost digit to be removed is more than 5, the preceding number is increased by 1. For example, 1.386. If we have to remove 6, we have to round it to 1.39. 2. If the rightmost digit to be removed is less than 5, the preceding number is not changed. For example, 4.334. If 4 is to be removed, then the result is rounded up to 4.33. 3. If the rightmost digit to be removed is 5, then the preceding number is not changed if it is an even number but it is increased by 1 if it is an odd number. For example, if 6.35 is to be rounded by removing 5, we have to increase 3 to 4 giving 6.4 as the result. However, if 6.25 is to be rounded off, it is rounded off to 6.2. 1.4.3 Dimensional analysis. Often while calculating, there is a need to convert units from one system to the other. The method used to accomplish this is called factor label method or unit factor method or dimensional analysis. This is illustrated below. Example: a piece of metal is 3 inch, represented by in, long. What is its length in cm? 2020 to 2114 Chemistry solution. We know that 1 in equals 2.54 centimeters. From this equivalence, we can write 1 in equals 1 equals 2.54 centimeters, 2.54 centimeters, 1 in 2.54 centimeters. Thus, 2.54 centimeters equals 1 and 1 in also equals 1. Both of these are called unit factors. If some number is multiplied by these unit factors, i.e., 1, it will not be affected otherwise. Say, the 3 in given above is multiplied by the unit factor. So, 2.54 centimeters 3 in equals 3 in times 1 in equals 3 times 2.54 centimeters equals 7.62 centimeters. Now, the unit factor by which multiplication 2.54 centimeters is to be done is that unit factor, 1 in the above case, which gives the desired units, i.e., the numerator should have that part which is required in the desired result. It should also be noted in the above example that units can be handled just like other numerical part. It can be cancelled, divided, multiplied, squared, etc. Let us study one more example. Example: a jug contains 2 L of milk. Calculate the volume of the milk in M3. Solution: since 1 L equals 1000 cubic centimeters and 1 M equals 100 centimeters, which gives 1 M equals 100 centimeters 100 centimeters 1 M. To get M3 from the above unit factors, the first unit factor is taken and it is cubed. 1 M3 100 centimeters 1 cubic meter 106 centimeters 3 equals 1. 3 equals 1. Now 2L equals 2 times 1000 cm3. The above is multiplied by the unit factor 2 times 1000 cm3 times 1 cubic meter 106 cubic centimeters equals 2 cubic meters 103 equals 2 times 10-3 m3. Example: how many seconds are there in 2 days? Solution: here, we know 1 day equals 24 hours, h, or 1 day 24h equals 1 equals 24h 1 day. Then, 1h equals 60 minutes or 1h 60 minutes equals 1 equals 60 minutes 1h. So, for converting 2 days to seconds, i.e., 2 days equals seconds, the unit factors can be multiplied in series in one step only as follows: 2 day times 24h times 60 minutes times 60 s 1 day 1h 1 minute equals 2 times 24 times 60 times 60 s equals 172,800 s. 1.5 Laws of chemical combinations. The combination of elements to form compounds is governed by the following 5 basic laws. Antoine Lavoisier, 1743-1794. 1.5.1 Law of conservation of mass. This law was put forth by Antoine Lavoisier in 1789. He performed careful experimental studies for combustion reactions and reached to the conclusion that in all physical and chemical changes, there is no net change in mass during the process. Hence, he reached to the conclusion that matter can neither be created nor destroyed. This is called law of conservation of mass. This law formed the basis for several later developments in chemistry. In fact, this was the result of exact measurement of masses of reactants and products, and carefully planned experiments performed by Lavoisier. 2020-21 Some basic concepts of chemistry. 15 1.5.2 Law of definite proportions. This law was given by a French chemist, Joseph Proust. He stated that a given compound always contains exactly the same proportion of elements by weight. Proust worked with 2 samples of cupric carbonate, one of which was of natural Joseph Proust, 17541826, origin, and the other was synthetic. He found that the composition of elements present in it was same for both the samples as shown below, percent of copper carbon oxygen natural sample 51.359.74 synthetic sample 51.359.74 Thus, he concluded that irrespective of the source, a given compound always contains same elements combined together in the same proportion by mass. The validity of this law has been confirmed by various experiments. It is sometimes also referred to as law of definite composition. 1.5.3 Law of multiple proportions. This law was proposed by Dalton in 1803. According to this law, if two elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element, are in the ratio of small whole numbers. For example, hydrogen combines with oxygen to form two compounds, namely, water and hydrogen peroxide. Hydrogen and oxygen water 2 grams 16 grams 18 grams hydrogen and hydrogen peroxide 2 grams 32 grams 34 grams Here, the masses of oxygen, i.e., 16 grams and 32 grams, which combine with a fixed mass of hydrogen, 2 grams, bear a simple ratio, i.e., 16:32 or 1:2. 1.5.4 Gay-Lussac's Law of Gaseous Volumes. This law was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure. Thus, 100 ml of hydrogen combine with 50 ml of oxygen to give 100 ml of water. Joseph Louis Gay-Lussac vapor. Hydrogen and oxygen water 100 ml 50 ml 100 ml. Thus, the volumes of hydrogen and oxygen which combine, i.e., 100 ml and 50 ml, bear a simple ratio of 2:1. Gay-Lussac's discovery of integer ratio in volume relationship is actually the law of definite proportions by volume. The law of definite proportions, stated earlier, was with respect to mass. The Gay-Lussac's law was explained properly by the work of Avogadro in 1811. 1.5.5 Avogadro's law. In 1811, Avogadro proposed that equal volumes of all gases at the same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atoms and molecules which is quite understandable in present times. If we consider again the reaction of hydrogen and oxygen to produce water, we see that 2 volumes of hydrogen combine with 1 volume of oxygen to give 2 volumes of water without leaving any unreacted oxygen. Note that in the Fig 1.9, page 16, each box contains equal number of molecules. In fact, Avogadro could explain the above result by considering the molecules to be polyatomic. If hydrogen and oxygen were considered as diatomic as recognized now, then the above results are easily understandable. However, Dalton and others believed at that time that atoms of the Lorenzo Romano Amadeo Carlo Avogadro di Quercia e di Carato, 1776186, 2020-2116 Chemistry Fig 1.92 volumes of hydrogen react with 1 volume of oxygen to give 2 volumes of water vapor same kind cannot combine and molecules of oxygen or hydrogen containing 2 atoms did not exist. Avogadro's proposal was published in the French Journal de Physique. In spite of being correct, it did not gain much support. After about 50 years, in 1860, the first international conference on chemistry was held in Karlsruhe, Germany, to resolve various ideas. At the meeting, Stanislaw Cannizzaro presented a sketch of a course of chemical philosophy, which emphasized on the importance of Avogadro's work. Dalton's theory could explain the laws of chemical combination. However, it could not explain the laws of gaseous volumes. It could not provide the reason for combining of atoms, which was answered later by other scientists. 1.7 Atomic and molecular masses. After having some idea about the terms atoms and molecules, it is appropriate here to understand what do we mean by atomic and molecular masses. 1.6 Dalton's atomic theory. Although the origin of the idea that matter is composed of small indivisible particles called atomio, meaning indivisible, dates back to the time of Democritus, a Greek philosopher, 460-370 BC, it again started emerging as a result of several experimental studies which led to the laws mentioned above. In 1808, Dalton published a new system of chemical philosophy, in John Dalton, 1776-1884, which he proposed the following: 1. Matter consists of indivisible atoms. 2. All atoms of a given element have identical properties, including identical mass. Atoms of different elements differ in mass. 3. Compounds are formed when atoms of different elements combine in a fixed ratio. 4. Chemical reactions involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. 1.7.1 Atomic mass. The atomic mass or the mass of an atom is actually very small because atoms are extremely small. Today, we have sophisticated techniques, e.g., mass spectrometry, for determining the atomic masses fairly accurately. But in the 19th century, scientists could determine the mass of one atom relative to another by experimental means, as has been mentioned earlier. Hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1, without any units, and other elements were assigned masses relative to it. The present system of atomic masses is based on carbon-12 as the standard and has been agreed upon in 1961. Here, carbon-12 is one of the isotopes of carbon and can be represented as 12C. In this system, 12C is assigned a mass of exactly 12 atomic mass unit, AMU, and masses of all other atoms are given relative to the standard. One atomic mass unit is defined as a mass exactly equal 20 to 21. Some basic concepts of chemistry: 17 to 1/12 of the mass of one carbon, 12 atom. And 1 AMU equals 1.66056 times 1024 G. Mass of an atom of hydrogen equals 1.6736 times 1024 G. Thus, in terms of AMU, the mass of hydrogen atom equals 1.0078 AMU equals 1.0080 AMU. Similarly, the mass of oxygen, 16.160, atom would be 15.995 AMU. At present, AMU has been replaced by U, which is known as unified mass. When we use atomic masses of elements in calculations, we actually use average atomic masses of elements, which are explained below. 1.7.2 Average atomic mass. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance, percent occurrence, the average atomic mass of that element can be computed. For example, carbon has the following three isotopes with relative abundances and masses as shown against isotope relative abundance, percent. Atomic mass, AMU, 12C 98.892 1213C 1.108 13.00333514C 2 times 1010 14.00317 each of them. From the above data, the average atomic mass of carbon will come out to be 0.98892, 12U, plus 0.01108, 13.00335U, plus 2 times 1012, 14.00317U, equals 12.011U. Similarly, average atomic masses for other elements can be calculated. In the periodic table of elements, the atomic masses mentioned for different elements actually represent their average atomic masses. 1.7.3 Molecular mass. Molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. For example, molecular mass of methane, which contains one carbon atom and 4 hydrogen atoms, can be obtained as follows: molecular mass of methane, CH4, equals 12.011U, plus 4, 1.008U, equals 16.043U. Similarly, molecular mass of water, H2O, equals 2 times atomic mass of hydrogen plus 1 times atomic mass of oxygen equals 2, 1.008U, plus 16.00U equals 18.02U. 1.7.4 Formula mass. Some substances, such as sodium chloride, do not contain discrete molecules as their constituent units. In such compounds, positive, sodium ion, and negative, chloride ion, entities are arranged in a three-dimensional structure, as shown in Fig. 1.10. Fig. 1.10 Packing of Na and NCl ions in sodium chloride. It may be noted that in sodium chloride, one Na and ion is surrounded by 6 Cl ion and vice versa. The formula, such as NaCl, is used to calculate the formula mass instead of molecular mass, as in the solid-state sodium chloride does not exist as a single entity. 2020 to 2118 Chemistry. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine equals 23.0 U plus 35.5 U equals 58.5 U. Problem 1.1 Calculate the molecular mass of glucose, C6H12O6, molecule. Solution. Molecular mass of glucose, C6H12O6, equals 6, 12.011 U, plus 12, 1.008 U, plus 6, 16.00 U, equals 72.066 U, plus 12.096 U, plus 96.00 U, equals 180.162 U. 1.8 Mole concept and molar masses. Atoms and molecules are extremely small in size, and their numbers in even a small amount of any substance is really very large. To handle such large numbers, a unit of convenient magnitude is required. Just as we denote 1 dozen for 12 items, score for 20 items, gross for 144 items, we use the idea of mole to count entities at the microscopic level, i.e., atoms, molecules, particles, electrons, ions, etc. In SI system, mole, symbol, mole, was introduced as seventh base quantity for the amount of a substance. The mole, symbol mole, is the SI unit of amount of substance. 1 mole contains exactly 6.02214076 times 1023 elementary entities. This number is the fixed numerical value of the Avogadro constant, Na, when expressed in the unit mole 1, and is called the Avogadro number. The amount of substance, symbol N, of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, any other particle or specified group of particles. It may be emphasized that the mole of a substance always contains the same number of entities, no matter what the substance may be. In order to determine this number precisely, the mass of a carbon-12 atom was determined by a mass spectrometer and found to be equal to 1.992648 times 1023 g. Knowing that 1 mole of carbon weighs 12 grams, the number of atoms in it is equal to 12 grams/mole 12 C. 1.992648 times 10 to 23 grams/12 C. Atom equals 6.022137 times 1023 atoms/mole. This number of entities in 1 mole is so important that it is given a separate name and symbol. It is known as Avogadro constant, or Avogadro number, denoted by Na in honor of Amedeo Avogadro. To appreciate the largeness of this number, let us write it with all zeros without using any powers of 10. 60221367000000000000000000. Hence, so many entities, atoms, molecules, or any other particle, constitute 1 mole of a particular substance. We can, therefore, say that 1 mole of hydrogen atoms equals 6.022 times 1023 atoms. 1 mole of water molecules equals 6.022 times 1023 water molecules. 1 mole of sodium chloride equals 6.022 times 1023 formula units of sodium chloride. Having defined a mole, it is easier to know the mass of 1 mole of a substance or the constituent entities. The mass of 1 mole of a substance in grams is called its molar mass. The molar mass in grams is numerically equal to atomic/molecular/formula mass in U. Molar mass of water equals 18.02 grams mole 1. Molar mass of sodium chloride equals 58.5 grams mole 1. 1.9% composition. So far, we were dealing with the number of entities present in a given sample. But many a time, information regarding the percentage of a particular element present in a compound is required. Suppose, an unknown or new compound is given to you. The first question: Fig 1.111 mole of various substances 2020-21. Some basic concepts of chemistry 19. You would ask is, what is its formula, or what are its constituents, and in what ratio are they present in the given compound? For known compounds also, such information provides a check whether the given sample contains the same percentage of elements as present in a pure sample. In other words, one can check the purity of a given sample by analyzing this data. Let us understand it by taking the example of water, H2O. Since water contains hydrogen and oxygen, the percentage composition of both these elements can be calculated as follows: mass percent of an element equals mass of that element in the compound times 100 molar mass of the compound. Molar mass of water equals 18.02 grams. Mass percent of hydrogen equals 11.18. Mass percent of oxygen equals 16.00 times 100. 18.02 equals 88.79. Let us take one more example. What is the percentage of carbon, hydrogen, and oxygen in ethanol? Molecular formula of ethanol is C2H5O. Molar mass of ethanol is 2 times 12.01 plus 6 times 1.008 plus 16.00, G equals 46.068 grams. Mass percent of carbon equals 24.02 grams. 46.068 grams times 100 equals 52.14%. Mass percent of hydrogen equals 6.048 grams. 46.068 grams times 100 equals 13.13%. Mass percent of oxygen equals 16.00 grams. 46.068 grams times 100 equals 34.73%. After understanding the calculation of percent of mass, let us now see what information can be obtained from the percent composition data. 1.9.1 Empirical formula for molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in a molecule of a compound. If the mass percent of various elements present in a compound is known, its empirical formula can be determined. Molecular formula can further be obtained if the molar mass is known. The following example illustrates the sequence. Problem 1.2. A compound contains 4.07% hydrogen, 24.27% carbon, and 71.65% chlorine. Its molar mass is 98.96 grams. What are its empirical and molecular formulas? Solution. Step 1. Conversion of mass percent to grams. Since we are having mass percent, it is convenient to use 100 grams of the compound as the starting material. Thus, in the 100 gram sample of the above compound, 4.07 grams hydrogen, 24.27 grams carbon, and 71.65 grams chlorine are present. Step 2. Convert into number moles of each element. Divide the masses obtained above by respective atomic masses of various elements. This gives the number of moles of constituent elements in the compound. 4.07 grams moles of hydrogen equals 1.008 grams equals 4.04 moles of carbon equals 24.27 grams. 12.01 grams equals 2.021 moles of chlorine equals 71.65 grams. 35.453 grams equals 2.021. 2020 to 2120 Chemistry. Step 3. Divide each of the mole values obtained above by the smallest number amongst them. Since 2.021 is smallest value, division by it gives a ratio of 2:1:1 for HCCl. In case the ratios are not whole numbers, then they may be converted into whole number by multiplying by the suitable coefficient. Step 4. Write down the empirical formula by mentioning the numbers after writing the symbols of respective elements. CH2Cl is, thus, the empirical formula of the above compound. Step 5. Writing molecular formula. A. Determine empirical formula mass by adding the atomic masses of various atoms present in the empirical formula. For CH2Cl, empirical formula mass is 12.01 plus 2 times 1.008 plus 35.453 equals 49.48 grams. B. Divide molar mass by empirical formula mass equals 2 equals N. C. Multiply empirical formula by N obtained above to get the molecular formula. Empirical formula equals CH2Cl, N equals 2. Hence molecular formula is C2H4Cl2 available from the balanced chemical equation of a given reaction. Let us consider the combustion of methane. A balanced equation for this reaction is as given below: CH4, G, plus 2O2, G, CO2, G, plus 2H2O, G. Here, methane and dioxygen are called reactants and carbon dioxide and water are called products. Note that all the reactants and the products are gases in the above reaction, and this has been indicated by letter G in the brackets next to its formula. Similarly, in case of solids and liquids, S and L are written respectively. The coefficients 2 for O2 and H2O are called stoichiometric coefficients. Similarly, the coefficient for CH4 and CO2 is 1 in each case. They represent the number of molecules, and moles as well, taking part in the reaction or formed in the reaction. Thus, according to the above chemical reaction, 1 mole of CH4, G, reacts with 2 moles of O2, G, to give 1 mole of CO2, G, and 2 moles of H2O, G. 1 molecule of CH4, G, reacts with 2 molecules of O2, G, to give 1 molecule of CO2, G, and 2 molecules of H2O, G. 22.7 L of CH4, G, reacts with 45.4 L of O2, G, to give 22.7 L of CO2, G, and 45.4 L of H2O, G. 16 grams of CH4, G, reacts with 2 times 32 G of O2, G, to give 44 grams of CO2, G, and 2 times 18 G of H2O, G. From these relationships, the given data can be interconverted as follows: 1.10 Stoichiometry and stoichiometric calculations. The word stoichiometry is derived from 2 Greek words stoichion, meaning element, and metron, meaning measure. Stoichiometry, thus, deals with the calculation of masses, sometimes volumes also, of the reactants and the products involved in a chemical reaction. Before understanding how to calculate the amounts of reactants required or the products produced in a chemical reaction, let us study what information is mass equals density volume. 1.10.1 Limiting reagent. Many a time, reactions are carried out with the amounts of reactants that are different than the amounts as required by a balanced chemical reaction. In such situations, one reactant is in more amount than the amount required by balanced chemical reaction. The reactant which is present in the least amount 20 to 21. Some basic concepts of chemistry. 21 gets consumed after some time, and after that further reaction does not take place whatever be the amount of the other reactant. Hence, the reactant, which gets consumed first, limits the amount of product formed and is, therefore, called the limiting reagent. In performing stoichiometric calculations, this aspect is also to be kept in mind. 1.10.2 Reactions in solutions. A majority of reactions in the laboratories are carried out in solutions. Therefore, it is important to understand as how the amount of substance is expressed when it is present in the solution. The concentration of a solution or the amount of substance present in its given volume can be expressed in any of the following ways. 1 mass percent or weight percent, W/W percent. 2 mole fraction 3. Molarity 4. Molality. Let us now study each one of them in detail. Balancing a chemical equation. According to the law of conservation of mass, a balanced chemical equation has the same number of atoms of each element on both sides of the equation. Many chemical equations can be balanced by trial and error. Let us take the reactions of a few metals and nonmetals with oxygen to give oxides 4Fe, S, 2Mg, S, P4, S, plus 3O2, G, plus O2O, G2, G, 2Fe2O3, S, 2MgO, S, P4O10, S, A, balanced equation, B, balanced equation, C, unbalanced equation. Equations, A, and, B, are balanced, since there are same number of metal and oxygen atoms on each side of the equations. However, equation, C, is not balanced. In this equation, phosphorus atoms are balanced but not the oxygen atoms. To balance it, we must place the coefficient 5 on the left of oxygen on the left side of the equation to balance the oxygen atoms appearing on the right side of the equation. P4, S, plus 5O2, G, P4O10, S, balanced equation. Now, let us take combustion of propane, C3H8. This equation can be balanced in steps. Step 1. Write down the correct formulas of reactants and products. Here, propane and oxygen are reactants, and carbon dioxide and water are products. C3H8, G, plus O2, G, CO2, G, plus H2O, L, unbalanced equation. Step 2. Balance the number of C atoms, since 3 carbon atoms are in the reactant, therefore, 3 CO2 C3H8 molecules, G, plus O2, G, are required on the 3 CO2, G, plus H2O, L, right side. Step 3. Balance the number of H atoms. On the left there are 8 hydrogen atoms in the reactants. However, each molecule of water has 2 hydrogen atoms, so 4 molecules of water will be required for 8 hydrogen atoms on the right side. C3H8, G, plus O2, G, 3 CO2. Step 4. Balance the number of G, plus 4 H2OO atoms, L. There are 10 oxygen atoms on the right side. 3 times 2 equals 6 in CO2 CO2 and 4 4 times 1 equals 4 4 in water. Water. Therefore, 5 O2 molecules are needed to supply the required 10. Therefore, 5 O2 molecules are needed to supply the required 10 oxygen atoms. C3H8, G, plus 5 O2, G, 3 CO2, G, plus 4 H2O, L. Step 5. Verify that the number of atoms of each element is balanced in the final equation. The equation shows 3 carbon atoms, 8 hydrogen atoms, and 10 oxygen atoms on each side. All equations that have correct formulas for all reactants and products can be balanced. Always remember that subscripts in formulas of reactants and products cannot be changed to balance an equation. 2020 to 2122 Problem 1.3 Calculate the amount of water, G, produced by the combustion of 16 grams of methane. Solution. The balanced equation for the combustion of methane is CH4, G, plus 2O2, G, CO2, G, plus 2H2O, G, I, 16 G of CH4 corresponds to 1 mole. 2. From the above equation, 1 mole of CH4, G, gives 2 mole of H2O, G. 2 mole of water, H2O, equals 2 times, 2 plus 16, equals 2 times 18 equals 36 grams. 1 mole H2O equals 18 grams H2O. 18 grams H2O. 1 mol H2O equals 118 grams H2O. Hence, 2 mole H2O times 1 mol H2O equals 2 times 18 grams H2O equals 36 grams H2O. Problem 1.4 How many moles of methane are required to produce 22 grams CO2, G, after combustion? Solution. According to the chemical equation, CH4, G, plus 2O2, G, CO2, G, plus 2H2O, G, 44 grams CO2, G, is obtained from 16 grams CH4, G. 1 mole CO2, G, is obtained from 1 mole of CH4, G. Number of moles of CO2, G, 1 mol CO2, G, equals 22 grams CO2, G, times 44 grams CO2, G, equals 0.5 mole CO2, G, hence, 0.5 mole CO2, G, would be obtained from 0.5 mole CH4, G, or 0.5 mole of CH4, G, would be required to produce 22 grams CO2, G. Problem 1.5 50.0 kilograms of N2, G, and 10.0 kilograms of H2, G, are mixed to produce NH3, G. Calculate the amount of NH3, G, formed. Identify the chemistry limiting reagent in the production of NH3 in this situation. Solution: A balanced equation for the above reaction is written as follows: calculation of moles. Number of moles of N2 equals 50.0 kilograms N2 times 1000 grams N2 1 kilogram N2 times 1 mol N2 28.0 grams N2 equals 17.86 times 102 mole. Number of moles of H2 equals 10.00 kilograms H2 times 1000 1 kilogram GH2 H2 times 1 mol H2 2.016 grams H2 equals 4.96 times 103 mole. According to the above equation, 1 mole N2, G, requires 3 mole H2, G, for the reaction. Hence, for 17.86 times 102 mole of N2, the moles of H2, G, required would be 17.86 times 102 mole N2 times 3 1 mole H2 N2, G, G, equals 5.36 times 103 mole H2, but we have only 4.96 times 103 mole H2. Hence, dihydrogen is the limiting reagent in this case. So, NH3, G, would be formed only from that amount of available dihydrogen, i.e., 4.96 times 103 mole, since 3 mole H2, G, gives 2 mole NH3, G, 4.96 times 103 mole H2, G, times 2 mole NH3, G, 3 mole H2, G, equals 3.30 times 103 mole NH3, G, 3.30 times 103 mole NH3, G, is obtained. If they are to be converted to grams, it is done as follows: 1 mole NH3, G, equals 17.0 grams NH3, G, 3.30 times 103 mole NH3, G, times 17.0 grams NH3, G, 1 mol NH3, G, 2020-21. Some basic concepts of chemistry. 23 equals 3.30 times 103 times 17 G NH3, G, equals 56.1 times 103 G NH3 equals 56.1 kilograms NH3. 1. Mass percentage is obtained by using the following relation. Problem 1.6. A solution is prepared by adding 2 grams of a substance A to 18 grams of water. Calculate the mass percent of the solute. Solution 2. Mole fraction. It is the ratio of number of moles of a particular component to the total number of moles of the solution. If a substance A dissolves in substance B and their number of moles are Na and Nb, respectively, then the mole fractions of A and B are given as 3 molarity. It is the most widely used unit and is denoted by m. It is defined as the number of moles of the solute in 1 liter of the solution. Thus, molarity, m, equals no of moles of solute volume of solution in liters. Suppose we have 1 m solution of a substance, say NaOH, and we want to prepare a 0.2 m solution from it. 1 m NaOH means 1 mole of NaOH present in 1 liter of the solution. For 0.2 m solution, we require 0.2 moles of NaOH dissolved in 1 liter solution. Hence, for making 0.2 m solution from 1 m solution, we have to take that volume of 1 m NaOH solution, which contains 0.2 mole of NaOH, and dilute the solution with water to 1 liter. Now, how much volume of concentrated 1 m NaOH solution be taken, which contains 0.2 moles of NaOH, can be calculated as follows. If 1 mole is present in 1 L or 1000 ml solution, then 0.2 mole is present in 1000 ml times 0.2 mole solution 1 mol equals 200 ml solution. Thus, 200 ml of 1 m NaOH are taken and enough water is added to dilute it to make it 1 liter. In fact, for such calculations, a general formula, M1 times V1 equals M2 times V2, where M and V are molarity and volume, respectively, can be used. In this case, M1 is equal to 0.2 m, V1 equals 1000 ml, and M2 equals 1.0 m, V2 is to be calculated. Substituting the values in the formula, 0.2 m times 1000 ml equals 1.0 m times V2. Note that the number of moles of solute, NaOH, was 0.2 in 200 ml and it has remained the same, i.e., 0.2 even after dilution, in 1000 ml, as we have changed just the amount of solvent, i.e., water, and have not done anything with respect to NaOH. But keep in mind the concentration. 2020 to 2124 Problem 1.7 Calculate the molarity of NaOH in the solution prepared by dissolving its 4 grams in enough water to form 250 ml of the solution. Solution. Since molarity, m, note that molarity of a solution depends upon temperature because volume of a solution is temperature dependent. For molality, it is defined as the number of moles of solute present in 1 kilogram of solvent. It is denoted by m. Thus, molality, m, equals No of moles of solute mass of solvent in kg. Chemistry. Problem 1.8 The density of 3m solution of NaCl is 1.25 grams ml1. Calculate the molality of the solution. Solution m equals 3 mol L1 mass of NaCl in 1L solution equals 3 times 58.5 equals 175.5 grams mass of 1L solution equals 1000 times 1.25 equals 1250 grams. Since density equals 1.25 grams ml1, mass of water in solution equals 1257. 5.5 equals 1074.5 grams. Molality equals No of moles of solute mass of solvent in kg equals 3 mol 1.0745 kilograms equals 2.79 m. Often in a chemistry laboratory, a solution of a desired concentration is prepared by diluting a solution of known higher concentration. The solution of higher concentration is also known as stock solution. Note that the molality of a solution does not change with temperature since mass remains unaffected with temperature. Summary. Chemistry, as we understand it today, is not a very old discipline. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied the knowledge in various walks of life. The study of chemistry is very important as its domain encompasses every sphere of life. Chemists study the properties and structure of substances and the changes undergone by them. All substances contain matter, which can exist in 3 states: solid, liquid or gas. The constituent particles are held in different ways in these states of matter and they exhibit their characteristic properties. Matter can also be classified into elements, compounds, or mixtures. An element contains particles of only one type, which may be atoms or molecules. The compounds are formed where atoms of 2 or more elements combine in a fixed ratio to each other. Mixtures occur widely and many of the substances present around us are mixtures. When the properties of a substance are studied, measurement is inherent. The quantification of properties requires a system of measurement and units in which the quantities are to be expressed. Many systems of measurement exist, of which 2020 to 21 some basic concepts of chemistry, 25 the English and the metric systems are widely used. The scientific community, however, has agreed to have a uniform and common system throughout the world, which is abbreviated as SI units, International System of Units. Since measurements involve recording of data, which are always associated with a certain amount of uncertainty, the proper handling of data obtained by measuring the quantities is very important. The measurements of quantities in chemistry are spread over a wide range of 1031 to 10 plus 23. Hence, a convenient system of expressing the numbers in scientific notation is used. The uncertainty is taken care of by specifying the number of significant figures, in which the observations are reported. The dimensional analysis helps to express the measured quantities in different systems of units. Hence, it is possible to interconvert the results from one system of units to another. The combination of different atoms is governed by basic laws of chemical combination, these being the law of conservation of mass, law of definite proportions, law of multiple proportions, Gay-Lussac's law of gaseous volumes and Avogadro law. All these laws led to the Dalton's atomic theory, which states that atoms are building blocks of matter. The atomic mass of an element is expressed relative to 1,2C isotope of carbon, which has an exact value of 1,2U. Usually, the atomic mass used for an element is the average atomic mass obtained by taking into account the natural abundance of different isotopes of that element. The molecular mass of a molecule is obtained by taking sum of the atomic masses of different atoms present in a molecule. The molecular formula can be calculated by determining the mass percent of different elements present in a compound and its molecular mass. The number of atoms, molecules, or any other particles present in a given system are expressed in the terms of Avogadro constant, 6.022 times 1023. This is known as 1 mole of the respective particles or entities. Chemical reactions represent the chemical changes undergone by different elements and compounds. A balanced chemical equation provides a lot of information. The coefficients indicate the molar ratios and the respective number of particles taking part in a particular reaction. The quantitative study of the reactants required or the products formed is called stoichiometry. Using stoichiometric calculations, the amount of one or more reactant, S, required to produce a particular amount of product can be determined and vice versa. The amount of substance present in a given volume of a solution is expressed in number of ways, e.g., mass percent, mole fraction, molarity, and molality. Exercises 1.1 Calculate the molar mass of the following: I, H2O, 2, CO2, 3, CH4. 1.2 Calculate the mass percent of different elements present in sodium sulfate, Na2SO4. 1.3 Determine the empirical formula of an oxide of iron, which has 69.9% iron and 30.1% dioxygen by mass. 1.4 Calculate the amount of carbon dioxide that could be produced when 1 mole of carbon is burned in air. 2. 1 mole of carbon is burnt in 16 grams of dioxygen. 3. 2 moles of carbon are burnt in 16 grams of dioxygen. 1.5 Calculate the mass of sodium acetate, CH3COONA, required to make 500 ml of 0.375 molar aqueous solution. Molar mass of sodium acetate is 82.0245 grams mole 1. 2020 to 2126 Chemistry 1.6 1.7 1.8 1.9 1.10 1.11 1.12 1.13 1.14 1.15 1.16 1.17 1.18 1.19 Calculate the concentration of nitric acid in moles per liter in a sample which has a density 1.41 grams ml1 and the mass percent of nitric acid in it being 69%. How much copper can be obtained from 100 grams of copper sulfate, CuSO4? Determine the molecular formula of an oxide of iron, in which the mass percent of iron and oxygen are 69.9 and 30.1, respectively. Calculate the atomic mass, average, of chlorine using the following data: percent natural abundance molar mass 35Cl 75.77 34.968937 Cl 24.23 36.9659 in 3 moles of ethane, C2H6. Calculate the following: I, number of moles of carbon atoms. 2, number of moles of hydrogen atoms. 3, number of molecules of ethane. What is the concentration of sugar, C12H22O11, in mole L1 if its 20 grams are dissolved in enough water to make a final volume up to 2L? If the density of methanol is 0.793 kg L1, what is its volume needed for making 2.5 L of its 0.25 m solution? Pressure is determined as force per unit area of the surface. The SI unit of pressure, Pascal, is as shown below. 1 Pa equals 1 nm2 if mass of air at sea level is 1034 grams cm2. Calculate the pressure in Pascal. What is the SI unit of mass? How is it defined? Match the following prefixes with their multiples. Prefixes multiples: I, micro 106, 2, deca 109, 3, mega 106, 4, giga 1015, V, Femto 10. What do you mean by significant figures? A sample of drinking water was found to be severely contaminated with chloroform, CHCl3, supposed to be carcinogenic in nature. The level of contamination was 15 ppm, by mass. I. Express this in percent by mass. 2. Determine the molality of chloroform in the water sample. Express the following in the scientific notation: I. 0.0048, 2. 234,000, 3. 8008, 4. 500.0, v. 6.0012. How many significant figures are present in the following? I. 0.0025, 2. 208, 3. 5005. 2020-21. Some basic concepts of chemistry. 27. 1.20 1.21, a, b, 1.22 1.23 1.24 1.25 1.26 1.27, 4. 126,000, v. 500.0, 6. 2.0034. Round up the following up to 3 significant figures: I. 34.216, 2. 10.4107, 3. 0.04597, 4. 2808. The following data are obtained when dinitrogen and dioxygen react together to form different compounds. Mass of dinitrogen, mass of dioxygen: I. 14 grams 16 grams, 2. 14 grams 32 grams, 3. 28 grams 32 grams, 4. 28 grams 80 grams. Which law of chemical combination is obeyed by the above experimental data? Give its statement. Fill in the blanks in the following conversions: I. 1 kilometer equals mm equals pm, 2. 1 milligram equals kg equals ng, 3. 1 ml equals L equals dm. 3. If the speed of light is 3.0 times 108 ms1, calculate the distance covered by light in 2.00 ns. In a reaction A and B2 DAB2, identify the limiting reagent, if any, in the following reaction mixtures: I. 300 atoms of A plus 200 molecules of B, 2. 2 mole A plus 3 mole B, 3. 100 atoms of A plus 100 molecules of B, 4. 5 mole A plus 2.5 mole B, V. 2.5 mole A plus 5 mole B. Dinitrogen and dihydrogen react with each other to produce ammonia according to the following chemical equation: N2, G, plus H2, G, D2NH3, G, I. Calculate the mass of ammonia produced if 2.00 times 103 grams dinitrogen reacts with 1.00 times 103 G of dihydrogen. 2. Will any of the two reactants remain unreacted? 3. If yes, which one and what would be its mass? How are 0.50 mole Na2CO3 and 0.50 m Na2CO3 different? If 10 volumes of dihydrogen gas reacts with 5 volumes of dioxygen gas, how many volumes of water vapor would be produced? Convert the following into basic units: I. 28.7 pm, 2. 15.15 pm, 3. 25,365 milligrams. 2020-21. 28 Chemistry 1.28 1.29 1.30 1.31 1.32 1.33. Which one of the following will have the largest number of atoms? I. 1 gram O, S, 2. 1 gram Na, S, 3. 1 gram Li, S, 4. 1 gram of Cl2, G. Calculate the molarity of a solution of ethanol in water, in which the mole fraction of ethanol is 0.040, assume the density of water to be 1. What will be the mass of 112C atom in G? How many significant figures should be present in the answer of the following calculations? 0.02856 times 298.15 times 0.112, I. 0.5785, 3. 0.0125 plus 0.7864 plus 0.0215, 2, 5 times 5.364. Use the data given in the following table to calculate the molar mass of naturally occurring argon isotopes. Isotope 36Ar38Ar40Ar isotopic molar mass 35.967555 grams mole 137.96272 grams mole 139.9624 grams mole 1 abundance 0.337% 0.063% 99.600%. Calculate the number of atoms in each of the following: I. 52 moles of Ar, 2. 52 U of He, 3. 52 grams of He. 1.34. A welding fuel gas contains carbon and hydrogen only. Burning a small sample of it in oxygen gives 3.38 grams carbon dioxide, 0.690 grams of water and no other products. A volume of 10.0 L, measured at STP, of this welding gas is found to weigh 11.6 grams. Calculate I. Empirical formula, 2. Molar mass of the gas, and 3. Molecular formula. 1.35 1.36 calcium carbonate reaction, CaCO3, S, reacts with aqueous HCl plus 2HCl, Aq, CaCl2, Aq, 2 and give CaCl2 and CO2, G, plus H2O, L, CO2. According to the Watt mass of CaCO3 is required to react completely with 25 ml of 0.75 mHCl. Chlorine is prepared in the laboratory by treating manganese dioxide, MnO2, with aqueous hydrochloric acid. According to the reaction for HCl, Aq, plus MnO2, S, 2H2O, L, plus MnCl2, Aq, plus Cl2, G, how many grams of HCl react with 5.0 grams of manganese dioxide? 2020-21